Howdy everyone. Today we will be talking about two different searching algorithms. Namely, we will be talking about linear search algorithm and binary search algorithm. So let's get started with linear search algorithm. So linear search, what is it? So linear search is basically what you think of when you're searching through an array. You first look at index 0, and if that isn't it, you look through index 1, and if not that, you index 2. You're searching just one by one in order, nice and easy. So, worst case scenario, the item does not exist in this list at all. So let's say we're looking for 42. Well, we're going to look at this. 112 is not 42. This is not 42. No, 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 no. Boom. There's no 42, but we still had to look through the entire list before we could determine that. So because of that, the big O is big O of n, where n is the number of items. Obviously, this is inconsequential when the array is only 5. But imagine if the array was actually a billion items. Imagine you go through all the billion, and then it turns out that the list did not contain the number you were looking for. Now, of course, best case scenario is that your desired item is first in this list. So in this case, if I was looking for 112, boom, there's 112, we're done, we're finished. It took constant time, no problemo. Now, finally, the average case you're going to have is going to be theta of n. And this is when the item is in the middle of the list. So here we have theta n over 2. And through asymptotic notation, we know we can drop constants. So we're just going to drop the 1/2 to get theta of n in the end. Again, imagine average case, you're going to have like a 23 or a 12. And so you're going to look for that. And it's going to take half the time technically. But because we're looking at this notation, we'll say theta of n. I don't want you to memorize every one of these big O's, this omega and this theta. I want you to understand why it is the way it is. Because now, if you ask, what's the worst case for linear search, you can think, oh, well, the worst case scenario is you don't find it. And so then you can conclude that it's going to take O of n times. Or the best case is that it's like this first item. So really try to understand why this is the way it is. So next we have binary search. So binary search is done when every time you look through an item, through this list, you basically split it in half. So you just cut it in half. And importantly, the list has to be in some sort of order. This can be numerical, this can be alphabetical, this can be anything, as long as your program knows what order it is and how to determine if something's less than or greater than. So in this case, let's say we're looking for 85. What binary search is going to do is it's going to come here in the middle, and it's going to determine that 85 has to be in this right half of the list. So then it's going to chop off this left half. And then it's going to go to this right side, and once more, it's going to chop it off. It's going to look at this left side and this right side. And it's going to determine that 85 has to be in this left side. And on it goes until it chops it small enough until it finds 85. Now, the best case for this actually depends because there's different implementations you can do of binary search. Again, binary search just means that you're just splitting your list in half each time to find it. Okay. So here we have two different implementations. And here we're going to be searching for 11. So let's look at this to the left, right? We have a middle pointer, we have a low, and we have a high. And what's going to happen is that we're going to update these low and high in accordance to where this middle is. So this middle basically determines, it tells the code whether what you're searching for is to the left or to the right of it. So in this case, we have this middle option, and we know that 11 is less than 12. So we know that it has to be in this bottom half of the list. So we're going to move this high pointer down, and we're going to recalculate the middle pointer. So again, we move the high pointer down to where the middle was, and we recalculate the middle, where we find that it's 11. And again, we're going to see, is 11 less than 11? And again, since this is again false, we're going to again move this high down to where the middle and recalculate the mid pointer. And now we see that we've gone too far, So we're going to shift this low one back up. And now these two arrows are pointing in the same place. So we have found our search and we can exit out. Now notice how this while loop only exits until low is no longer less than high. So either they don't find anything. So that is, this is not actually 11. Let's say this was 10. Or if it actually finds it, if they convolve to the same point. Let's differentiate this from the right side. So again, we have a low, a high, and a mid pointer. Now notice here the key difference is that we can return mid right here. That is, if the middle is actually pointing to the value we're looking for, we just exit, we cancel. So this is going to be treated largely the same. Now, we know that 11 is down this left side. Notice how this high actually didn't point to the number 12. It pointed to the number 11. And the reason of this is because we know for a fact that this middle pointer is not pointing towards 11. And that's because of this last check here. Because if it had been pointing to 11, it would have just exited out as a success. Now again, we can recalculate the mid pointer. We know it has to be in the above section. So we recalculate and we find it, and now we exit out. Let's search for 12 this time. Okay, here we notice that the middle pointer is actually already pointing to 12. But in this first implementation, it does not matter. It does not care. So instead, we're going to have to go through the whole thing until low is not less than high. So again, I'm going to shift down our big arrow down. And then we're going to shift this blue arrow up because we've gone too far down. And again, they've convolved. Versus here in this right implementation, we know that this 12 is our value we found. We have else return mid. So we're done. We exit out. It took omega of 1 time in the best case scenario. So here's kind of here, if you looking at numbers better, we can see that version 1 is actually slower than version 2. You can see all the iterations that we went. And this makes sense, right? Because we're checking the middle each time. Because of that extra check to see if the middle is actually successful, then we can cut down on a bunch of work. So because of this, hopefully now you understand why the worst case is big O log 2 of n. Because worst case scenario, we don't find the list, right? But because we're splitting the items in half each time, we're not actually looking through the whole list. If we're going to search in this index for, let's say, 97, we're not going to look through the entirety of this list. In fact, we're going to ignore the entirety of like 0 through 1, right? Until we split it again. Because each time we're halving it. So because of this, in the worst case, it's going to take log 2 of n. Now, thank you for listening. If you have any questions or if you want any video on another topic, please let me know. This has been great.